Hey guys, I wanted to go over some of the basics of simple harmonic motion here. So should be seeing my screen here. I'm going to pull this up. You also have access to this Google presentation, but I just wanted to give it some narration here. So the motion we're studying is called simple harmonic motion. Harmonic means repeating over and over and over again. And simple means we're going to keep the rules pretty simple here, but there's a little bit more to it than that. By the way, a pendulum, which we did a virtual lab on the other day, that's pretty close. We're going to pretend it's totally simple harmonic motion. You can see the repeated motion over and over again as it is sloshing back and forth there. A mass on the end of a spring oscillating up and down or oscillating side to side. That's also a good example of simple harmonic motion. Or anything on a spring, like a bobblehead rocking back and forth, is a good example of simple harmonic motion. But it's got to be a little bit more than just repeating over and over and over again. So let's talk about the rules for simple harmonic motion. Because the moon going around the earth is a repeated motion over and over and over again, but it's not simple harmonic motion. And let's talk about why. So the moon would fit this first rule here. The motion is repeated, so it's cyclic. You get the same motion every single time once you get back to the beginning there. The second rule is that there is a force that is always towards the equilibrium point. That means there's some middle point where the object would like to be. For a pendulum, it's down exactly at the bottom. For a spring, it's where it would be resting if you just sort of gently set it there, and where it'll eventually come to a rest because of friction. So since this force is always towards the equilibrium, we call it a restoring force. And that's something that the moon lacks. The moon's force is always pulling it towards the center of the circle, sure, but it is not quite simple harmonic motion because it's not pushing it towards an equilibrium point, we would say. And the other reason that the moon doesn't fit this is this last one. The force is proportional to the displacement, meaning the further away you get from the equilibrium point, the stronger that force is, right? That wouldn't be true for the moon. The further away you get from the center of the earth, the weaker the force of gravity gets. So that would not be simple harmonic motion there. So those three rules has to be repeated. There has to be a force towards the equilibrium point called a restoring force. And that force has to get bigger with the, whoops, get out of here, JavaScript. Let's go back to here. So that force has to get bigger with displacement. You get twice as far away, the force is going to get twice as big. So here is a block on simple harmonic motion. We were at this position, x equals 0. We're going to displace it here to x equals negative a, and we're going to let it go. And it's going to swing out here to b, back to the middle point, overshoot that and get back to a on the other side. And then it's going to be pulled back, as the force indicates here, back to the middle, overshoot that, and get back to in position E here. We're basically repeated the cycle, and we're back to A. So a few points here. Distance is measured from the equilibrium point, not necessarily from where you start. So here we start the block from negative A, but the equilibrium point is what we'll call x equals 0. We call this maximum distance here the amplitude. So here we call it negative A because it's the amplitude to the left. And here we call it positive A because it's the amplitude to the right. A cycle is a full to and fro motion. So A to C to the other side is not a cycle. We have to go all the way to the other side and all the way back. So A to E is a full cycle. Remember this? This is a review, not a new bit of information. The period, which is symbolized with capital T, is the time required to complete one cycle. And also, this is a review, frequency, symbolized by lowercase f, is the number of cycles per second. And that's measured in hertz, remember. Cycles per second, we can just say with the word hertz. Remember this, that period is 1 over the frequency, and frequency is 1 over the period. So those two equations are not new, they are just review. All right, let's talk a few more things here about simple harmonic motion. First thing, let's think about some quantities out here at position A that are a maximum. So first thing that should be obvious, by definition, our displacement is a maximum. We define the amplitude as far away as you ever get. What else is also a maximum out there at our position A right here? Well, it's the force. Why? Well, let's go back to think about Hooke's law. Hooke's law says that the force is equal to kx. So more distance, which is what x stands for, more force. What else is a maximum at position A and C, by the way, both A and C? As long as you're as far away as you can get, right now we're not worried about direction. We're just worried about magnitude. Acceleration is also a maximum out here at A and C at the amplitudes. And that's because of Newton's second law. If the force is a maximum, since A equals F over m, then the acceleration is a maximum. One more thing is the elastic potential energy. So the energy stored in the spring is 1/2 kx squared. So again, if x is a maximum, then elastic potential energy is a maximum. Now, there are some things that are zero out at the amplitudes. What are those? Well, first of all, it's actually for an infinitely small moment in time not moving there. So it has no velocity at A and C. So since it has no velocity, there's two other things that are zero. Its kinetic energy is zero at A and C because kinetic energy is 1/2 mv squared. And its momentum is zero because momentum is mv. So what about here at point B? Well, everything basically gets flipped. So quantities that are zero at point B are the displacement, because that's where we define it to be zero position. Therefore, the force is zero, according to Hooke's law. Therefore, the acceleration is zero, according to Newton's second law. And therefore, the elastic potential energy is equal to zero. What's a maximum at the equilibrium point at position B here? The velocity is at a maximum because it's being pushed and pushed and pushed here and speeding up until it gets to this equilibrium position. But as soon as it overshoots it, it's going to actually, the spring's going to pull it back and start to slow it down. So its velocity is a maximum there. Therefore, its kinetic energy is a maximum. Therefore, its momentum is a maximum. Pendulums approximately, that should say they approximately represent simple harmonic motion. And that's really true. We say basically for theta is the angle, in other words, is less than 15 degrees. Then it's pretty much, you can consider it. After that, it gets a little off of there. You guys made some graphs the other day of different things that affect the period of a pendulum. So you can see here, the angle at first doesn't really affect it. Now, towards the end, it will start to affect it. You can see it shoots up here, but especially within these first 15 degrees here, there's really no effect of the angle hardly at all on the period. Here's another graph of the period versus mass. And given some error in data taking, there's really no effect of the mass on the period of a pendulum. Now, here's the period versus the length of the pendulum. And here you can see we get a fishing pole graph. A fishing pole graph is a square root graph. So when we put these together, this becomes the equation for the period of a pendulum. The period is equal to 2 pi times the square root of the length of the pendulum divided by gravity. So as long as we are here on Earth and we can't change g, then the only thing that affects the period of a pendulum is the length. Now, let's think about some proportional reasoning questions. If you doubled the length, what would that do to the period? Well, since the 2 would be under the radical, you would get square root 2 times more period, about 1.4. What if you quadrupled the length of your pendulum? Well, square root of 4 is 2. So you would have twice the length of period there. Masses oscillating on springs truly do represent simple harmonic motion because of Hooke's law. So what does that equation look like? Very similar. So here the period is equal to 2 pi radical, but instead of length, we've got mass now. So more mass is harder to pull. It's got more inertia, and therefore that will cause the period to be bigger. And then instead of dividing by gravity, we divide by the spring constant. A tougher spring will pull harder and reduce the period there. So let me show you this little video here. In this case, they took a mass on a spring and they attached a paint can to it. And then they're going to pull this piece of paper behind it. And there you'll be able to track where that paint can is as a function of time. What? All right, hold on. Let's watch it through here. you can see there that they get a perfect little sine wave or cosine wave, whatever you want to call it there. So it's tracing out a nice little sine wave there, and that is very important. So let's switch back here to our presentation. Stop that. Come back here. Watch this. So the pendulum here, again, imagine that it's tracing out. It's got a spray paint can on the back of it. You would trace out a nice little sine wave there that would look like that. So a few points about this. Here again, imagine that we started at the maximum amplitude and we let it go. Simple harmonic motion, position versus time graphs, we say are sinusoidal. Even if it's a cosine wave like right here, we'll just call it sinusoidal. So they follow this equation that x equals, and x is the position, a cosine 2 pi ft, or if we started it from the middle, it'd be x equals a sine 2 pi ft. So what are these things? Well, a is the amplitude, as you can see up here, our maximum distance, and f is frequency. So t is t and time, and x is position. So let's practice one right here. We're almost through this presentation. Here is a particular thing in simple harmonic motion, and we are tracking where it is as a function of time. So first thing is we can see that this is a sine graph. So we'll have to either pick sine or cosine. And so it's a sine graph, so we're going to follow this form. X equals a sine 2 pi ft. Next thing is we look on this graph, what's the amplitude? Well, we can see here the maximum distance it ever gets away is 15 centimeters. So the amplitude is 15 centimeters. Now let's find frequency. Well, we actually have to do a little step first. We can't see the frequency on here, but we can see the time. And if we look on here, this all the way to the peak, all the way to the bottom trough, and then back to the middle where we were here. That's a full cycle. Not here to here, because we haven't gone all the way down yet, here to here. So the time to get all the way around is 0.2 seconds. That's the period, or 1/5 of a second, right? So if the period is 1/5 of a second, then what's the frequency? Remember, the frequency and the period are inverses of each other. So if 1/5 of a second's the period, then flip that, 5 hertz is the frequency. And now we're ready to plug it all in. So now we can see that x equals our amplitude, 15 centimeters, times our sine function, times 2 pi. Now let's plug in for our frequency, 5 hertz times t. You might be like, what the heck is this? What is this even telling me? This will tell you the position now at any given moment in time. So for all infinity, as long as this thing's not slowed down, we can predict where this object is at any given moment in time. Let's do one more here. So here's a different graph. So first off, we have to pick whether it's a sine or cosine function, and we can see here that it's cosine. It starts at the peak. So we're going to build off of this equation right here. The amplitude we can read off of here is 6 centimeters this time, so a smaller amplitude. The period, look at this one, to get all the way from the top back up to the top. In this case, it took 0.4 seconds, or about 2/5, or not about, exactly 2/5 of a second. So if the period is 2/5 of a second, then flip that, the frequency is 5/2 of a hertz, or 2.5. So now we're ready to plug it into the equation. So x equals, our amplitude is 6 centimeters. We're using a cosine function, 2 pi, plug in for our f, is 2.5 hertz there. So that's it, and you guys are free to go.